Welcome back. Let's go through some units and equations. So it can be confusing at times in science when we have so many different quantities, right, with different symbols to represent them and different units as well. So mass, symbol M, units kilograms, right? So I have a mass of 70 kilograms, for example, and in a formula like kinetic energy, the mass is represented by the lowercase m. Time, symbol T, units seconds. Displacement, symbol D. You might see the symbol S as well, and it is in meters. Velocity, symbol V. You might also see it as a symbol for U, like initial velocity. Units meters per second. So ms to the -1 or m/s. Acceleration, symbol A, units meters per second squared. Force. Now force is quite a general term, but it's often symbolized with F, or like the weight force could be F and then subscript, so in small letters beneath it, W, or Fg, Fe, electrostatic, right? So F to represent force, and then you can specify with a subscript. Units for force are in newtons, capital N. So whenever a unit is named after someone, it is a capital letter. Torque, in level 2, we use tau. So this is Greek letter tau, so it's got a curve at the top and then a curve sort of at the bottom. So that's tau. You might also see it as capital T. And the units for torque, well, we know torque is force times distance, it's perpendicular. And so that's newtons, meters. So units are Newton meters. The spring constant often has the symbol K. And just looking at Hooke's law, if we rearranged for K, it would be force divided by distance. So force is in newtons, divided by distance, which is in meters. So the unit would be newtons per meter. Right, and see how that's quite similar to torque. However, it's newtons per meter rather than Newton meters. Momentum, lowercase p. Right? Why is it not uppercase? Well, because of course power is uppercase P. Yeah, it does get confusing. So momentum, lowercase p. Well, momentum is mass times velocity, where mass is in kilograms and velocity is in meters per second. So momentum would have units kilograms, meters per second. Kilogram, meters per second. It also, you might recall this equation for impulse, change in momentum, force times time. It also has an equivalent unit, Newton seconds. Right? And I encourage you to try work out why these two are related by thinking about force being mass times acceleration. Right? You can actually show that they are equivalent. That's why I love units so much, because you can do what's called dimensional analysis, I believe. Basically, looking at the units, you can work out a lot of interesting things. Onwards. Oh, there it is, impulse, which is change in momentum. So it's symbolized by capital delta, so a triangle, P for momentum. And again, the units are either kilogram meters per second or usually Newton seconds, but they are equivalent. So either works. Kinetic energy. often symbolized by capital E for energy and then lowercase k for kinetic. You may have seen KE, kinetic energy. This is a little bit confusing because it seems like there should be a times in between. So it's better to write capital E for energy and then subscript K to specify the type, right? Just like we did for the forces. Or if in doubt, you can actually just write out the word kinetic energy. Now, what are the units? So energy is measured in joules. And you can actually express joules, right? Think about kinetic energy is half mass times v squared. So that's kilograms, meters per second squared. So kilograms meters squared per second squared is the same unit as joules, right? But that gets a bit messy, which is why we just use joules. Elastic potential energy. So it's a form of an energy, so capital E, but then lowercase p. And it also has units, joules. Work, capital W. Now work is defined from a formula as force times distance, where the force and distance are in the same direction, right, compared to torque, where they are perpendicular. And so we might say it should be Newton meters as well, right? Force times distance. So that is a valid unit. However, work is better defined as the energy transferred, which, if we're talking about energies, would be in joules. Yeah, but either work. And lastly, capital P for power. We know power is work or energy over time, where work is in joules, time is in seconds, so the units would be joules per second, or capital W for watts. And now, you're seeing why this is confusing? Because capital W is the symbol for work, but the unit for watts. So, if you like, you can actually just write joules per second as the units for power, or watts. All right, and it's a capital W named after a person. Okay, that is all of the quantities in level 2 mechanics, their symbols and units. Part B. Sometimes, if the question's a bit mean to you, it doesn't give you the quantities in SI units, and you need to convert them first, right? Before you can use any of your equations, convert them to SI units. So let's do that together now. So 250 grams. Actually, grams is an interesting one. It's, I believe, the only SI unit where it has a prefix, like, because mass is kilograms. However, all the other ones don't have like kilo or mega or anything in front of them. And it has a very interesting story that you should definitely look up. So look up, why does mass have SI units kg and not g? Alright, 250 grams, we can divide by 1,000 to get 0.25 kilograms. Yeah. 100 kilometers per hour. I'll show you the shortcut and then I'll show you the where it comes from. So to get into meters per second, we divide by 3.6. So about 28 meters per second. And so where that comes from, so 100 kilometers per 1 hour, there are 1,000 meters for every 1 kilometer, right? So we times it by 1,000. But there are 3,600 seconds for every 1 hour. And so you'll notice, so this was the original amount, 100, and we're timesing it by, what is that? 10 over 36, or 1 over 3.6, which is the same as dividing it by 3.6. Yeah, and when we go the other way, from meters per second to kilometers per hour, we would times it by 3.6. All right, 8 millimeters. Milli means times 10 to the power of -3, which you could then write out as decimal, or you could leave as scientific notation like this. What's next? Kilometers. 12.34 kilometers is 12.34. Now kilo is times 10 to the power of +3. So timesing by 1,000 meters. Again, you can leave it in this form, or you could write out the full number. Next up, we have 1,000 kilonewtons. Well, we know kilo is 1,000, so we have 1,000. So 1,000 times 1,000 newtons. And again, you can punch this in on your calculator to get the value. I'm just leaving it as in exponential form. What's next? Oh, 24 Newton centimeters. So what quantity is that measuring? So it's not a distance, it's a force times a distance. So that could be torque, or it could be work done, right? It's either of those properties. So newtons is already in SI units, but we need centimeters into meters. So we would need to divide it by 100, or times it by 10 to the power of -2. That will give us the answer in Newton meters. So 0.24 Newton meters. 7.8 megajoules. I do love saying megajoules. Mega means million, so it's 7.8 million joules. And lastly, 1.11 kilowatts. Again, kilo is 1,000, so it's 1.11 times 1,000 watts. And that's all done. That is quite a lot, I know, but hopefully this helped you out a little bit. And the best way is to just try problems and think about the units as well, to make sure that your final answer is in the correct units, right? So it lines up with the other units as well. And see you next time.